Hey everybody. In today's video we're going to talk about how you measure linear association. How do we measure if things are correlated? I mean, we can kind of look at it and say, well, that looks like there's a pattern. But basically the only time that we can see a pattern is when it's blatantly obvious. And so we need some kind of measure to say how well correlation works. And this is going to be for linear correlation. And so that's what we're going to be talking about today. There's a coefficient R, and it measures the strength of a linear relationship between two quantitative variables. And I even don't necessarily like the way this is written. R value is not how linear the data is, it's how well a linear model fits the data. And that's very important. It's not saying the data is linear, it's just saying that a linear model can fit it. And we'll get into why that distinction has to be made a little bit later. So R is always going to be a number between -1 and 1. If you ever get an R value that's different, an R of 1 is perfect. All the points are a perfect line with positive slope. A correlation of -1 is a line with all the points lie on a single line with negative slope. Anything off of those two is some shade of gray where they're not perfectly linear, but there's a linear pattern seems to fit them okay. The closer you get to 0, the weaker the relationship is. And so R values, and R is, once again, R values with positive R values are positive linear relationships, and negative R values indicate a negative linear relationship. Remember, once again, the negative is not putting any type of emphasis on whether it's a good outcome for society. It's merely saying positive as one variable goes up, the other variable goes up. Negative as one variable goes up, the other variable goes down. So the closer you are to 0, the weaker it is. The closer you get to -1 or 1, the stronger it is. And like we said before, the extreme value of -1 and 1 only occurs in a perfect linear relationship. And so here's an example of this, and this is just some R values. This top one here is an R value of 0. There is no pattern whatsoever. This would be weak negative linear relationship. This would be a moderate positive relationship. And if you look at it, it's really hard to tell the difference between these two by looking at them. And is this one really that much more? Can you see a pattern in this one much better than you can see a pattern in this one? And it's not really, and that's why we need the R values. And then we start to see this. So if you see this, right, see this -0.7, that's moderately strong correlation, 0.7. And then 0.9 is very strong, and 0.99 is like ridiculously strong correlation. And so that's what R value is, and we'll see more examples of this. So how do you find R? Well, luckily we have technology these days. And I'll show you how we calculate it. So let's look at this. This is the formula for R. It's the sum of the difference of every point from x bar. Remember, so you would take all your points that you have, and you would create x bar, and you'd find the average x value. And then you would subtract each point x value from the average x value, and then divide it by the standard deviation of the x's. Then you would do the same thing for the corresponding y point. Then you'd multiply those together, and then you would do that for every single point. And so, if you're trying to find correlation of 10 or 12 points, you'd have to do this, if you're 10 points, and then you would multiply it by 1 over n minus 1. The good news is that we will never, ever, ever ask you to do this by hand. But basically, it's looking at how much each point deviates from the average points of all of them. And so the key points here is, in order to do this, you would have to do the one variable stats on the x's. and then do the one variable stats on the y's. So you would get the average y value and the average and the standard deviations of the x's and the y's. How correlation behaves is more important than the details of the formula. So here are some important ideas. And this is if we go back to this, I'll show you some interesting things. Which is, whatever the units on this are going to be the units on this, which are going to be the units on this. So if you've ever done any unit analysis, the units would cancel. And that's going to be the same thing here, is that the units would cancel. So the first big takeaway is that the correlation coefficient has no unit of measurement. There's no units on it. It's just a number. The other thing that's interesting in that is, because of that same thing, any change in units you would make to the top and the bottom of the fraction, which is really just multiplying by 1. So changing units does not change R. So if we were doing the correlation between height in feet and shoe size, and then we changed to European shoe sizes and we changed to centimeters, the correlation the R value would stay the same even though the units changed. This is the big one. Correlation makes no difference between the explanatory and the response variable because we're multiplying them. All right, x and y. If we reverse these, you would get the exact same answer. And if we did this first and then this first, you'd get the exact same answer. And so correlation value, if you switch your axes, you will get the exact same R value. And so that's the correlation coefficient. The key thing here is that all variables must be quantitative. They both have to be something that measured. Nothing is categorical. If we're doing categorical data, we use a chi-square. Correlation does not describe curve relationships between variables, no matter how strong the relationship is. If we see that the data is curved, we do not talk about R. We do not. Correlation is not resistant. R is strongly affected by just a few outliers. One or two outliers will mess up R completely. And so we have to be observant of outliers in that situation. And correlation is not a complete summary of two variable data. There's a lot more going on. And so just to say the R value and not show the graph is inexcusable. Right? R value is something we add to the graph, not something we use in place of the graph. And we'll look at special cases of this one here tomorrow. I will show you examples of where we can get very high R values from non-linear data. Data that is clearly not a straight line, and we can get very high R values. And so we should never use the R value as a measure of how linear the data is. And that's another reason you can't use correlation as a summary, because you want to see the data. And we want to see whether the data is linear before we even comment on the R values. So short video today, which is good because you should be working on your review stuff for the AP exam as well.